Okay, we good? All right, let's do this. So, hello, thanks for joining us in the main seminar room for our first, I think it's our first in person since COVID. So, welcome back. Woohoo! All right, it's my pleasure to introduce today's speaker from University of Michigan, Richard or Ricky B. Rude. He's going to be presenting Rethinking How We Plan Weather and Climate Modeling Strategies. Can we better fit models for purpose? I know the answer to that one already. Ricky holds a bachelor's in physics from University of North Carolina, a master's in meteorology from Florida State University, as well as a PhD from Florida State. Beginning in 1992, Ricky held a series of leadership positions at NASA Goddard Space Flight Center, including head of data assimilation office, acting director of the NOAA-NASA Joint Center for Satellite Data Assimilation, and chief of the Computation and Information Science and Technology Office. During his time at NASA, he was focused on improving the organizational and functional effectiveness of the U.S. climate modeling efforts. He co-authored 2 reports on modeling strategies by the National Academy of Sciences and was also lead author of a document detailing modeling and computation strategies for the White House Office of Science and Technology Policy. And he also co-authored a book with Andrew Gettleman on climate modeling for laymen, known as Demystifying Climate Models. Until this year, Ricky was co-chair of the steering committee of NOAA's Unified Forecast System and has also served as a consultant for the National Weather Service with respect to their weather and predictive modeling efforts, as well as being a consultant for climate services at ECMWF. Beginning in 2005, he moved to University of Michigan, where he's currently advisor of their Masters of Engineering in Applied Climate, as well as the undergraduate advisor for climate impact study. Much of the work he does and the students in the center do is in collaboration with the Great Lakes Integrated Sciences and Assessment Center, known as GLISA. His research at U of M has focused on cross-disciplinary perspectives for climate change problem solving, with an emphasis on looking at the usability of climate projections for adaptation and preparedness planning. Some of the notable papers on this topic include Climate Projections and Their Impacts on Policy and Practice with Carmen Lemos, evaluating the appropriateness of downscaled climate information for projecting risks of salmonella, as well as Large Lakes and Climate Models, a Great Lakes case study on the usability of CMIP-5. He also contributes continually to the actionable science efforts at GLISA. So lastly, he co-owns a farm and runs a farm where he grows seasonal vegetable crops and looks after a flock of chickens, a trip of goats, and a rather inquisitive but very reserved llama. So Ricky is going to be staying with us for lunch. So if you're interested in joining us after the talk for a continued discussion, please meet us in the Mesa Lab cafeteria. All right, it's all yours.
Okay, thank you. And this is my last year of gainful employment. I'm retiring, and this is going to be my brand after I retire, and it's already been my brand for a little bit. So I want to give you a moment to adjust to the light. And I entitled this talk, Rethinking How We Plan Weather and Climate Model Strategies. Can we better fit models for purpose? I want to acknowledge a few people, Balaji, who he and I have been thinking about this and contemplating writing a paper on it for a few months now. And in the process of that, we've engaged with Kevin Reed. Monica contacted me, Allison Steiner, and Andrew Gettleman, and we've all been talking about this for a while, and I want to acknowledge their contributions. And this paper, actually, or this talk today, is a little bit of an outline of how things are evolving as we're chatting. So we're going to have personal background, which I'll go through very quickly because Monica just did it, but part of that is to establish credibility about some of the issues I'm going to be talking about. Then a background of this talk, an overview of U.S. weather and climate modeling very quickly, because there's some history there, and I can feel pretty confident that folks are not aware of that history, and that history is something that has an influence on what's happening right now. Should we continue to do things the same way? That has turned out to be a question of my whole career, which has both been rewarding at times, but probably has been more frustrating of how do we do things differently. And when I do that, I'm going to focus on climate modeling and CMIP. Then thesis and analysis, I'm going to propose a little idea, a use case based on adaptation, and then framing a plan.
Okay, then I'm message from
What?
Gunther just text me to say they cannot see the slide.
Yeah, is he on the YouTube or is he on the?
We cannot see
Can
the slide online, just the speaker. They just see you. Maybe.
No. I have a long experience of knowing that seeing me is not at all important.
Yeah, so the camera's just focusing. Hey, can we get the slides in the? Yeah, so like, or on the
because the people that are on YouTube.
they might need to pin the.
I think what has happened is that the camera is following my voice and that they have turned toward me.
Yeah, just pull it up on YouTube and see.
Yes.
Yeah, and they're streaming directly from YouTube. Sorry guys, it's the first time we've done it.
Because I bet that camera is supposed to be on the slide.
Hey, there we go. Yeah, that should be straight through that. Okay.
Oh,
Yeah.
okay, thank you. Okay, it works, go ahead.
Okay,
Okay, he said it works.
thank you. So I'm going to restate a little bit of my personal background because it's my experiential path. And I like to say that my experiential path gives me experience and expertise, but I'm not an expert in really anything except all this stuff meshed together. So training-wise, I was an atmospheric dynamicist, but the dynamicist thought I was a chemist. The chemist thought I was a dynamicist and somehow became a numerical modeler. Professionally, I was in the atmospheric chemistry and dynamics branch, and then I was the founding head of the data assimilation office, which is now the global modeling and assimilation office. Then I was the founding co-head of the Joint Center for Satellite Data Assimilation. And then I was the chief of the NASA Goddard Supercomputing Center, NCCS, and then SISTO. At Michigan, I made a deliberate change to get out of management and focused on climate change education, climate change problem solving, and public and professional communication. With regard to policy and modeling, in the late 1990s, I became involved with all the agencies and the Office of Science and Technology Policy after receiving 3 or 4 reports that they did not find usable, asked me to take the lead on writing a document on climate models and high-end computing. That contributed to the work I did on 2 National Academy committees on climate modeling, becoming an ECMWF external expert on the development of the climate services, and a consultant and co-lead for the Unified Forecast System. Somehow along this way, I became somebody associated with organizations and organizational change, which is one of the reasons that NOAA asked me into that Unified Forecast System. So my current research, if there's research, is actually on what is known as usability of climate knowledge and planning and management and adaptation. But the point here is what I'm going to present is perhaps an integration of all these different pieces, of which I have some experience, but I'm not expert in any of them. Quick background, Balaji and I had been thinking about this for a while. Monica asked my colleague and former student Laura Browley to talk in the workshop. Laura has quit doing this professionally, at least for a while. And so she got me, and I took it as an opportunity to start to think about how to frame the issues around modeling in CMIP. I was surprised at the number of comments I got from the talk at the workshop, the number of people who wrote me and who followed up with me. I then, a little bit at Balaji's urging, gave a talk at the Model Hierarchies Workshop at Stanford at the end of August, and today I'm starting a reframing of this, and this is definitely a work in progress. So, a little bit of an overview of U.S. weather and climate modeling. If we take a casual look, and I'm implicitly including hydrology at this point, within weather, NOAA has an operational mission in the United States on weather through the National Weather Service. Within research and services, we have NOAA, NCAR, NASA, Department of Defense, universities, and private sector, and the list could go on. Climate research and services, we have many of the same agencies, but then we add Department of Interior, Department of Energy, FEMA now. People need to appreciate that in the Biden administration, FEMA has a big mandate in climate change, and then universities and the private sector. Within each organization, there are likely to be several large and many small modeling activities. Many of them are similar. And I've heard each and every one of them argue that it is unique and deserving in some way. And this has ended up with a very highly fragmented approach to modeling, and our behavior suggests that this is the way we like it. It is difficult to deliver world-class products and services in this environment, and I want to emphasize this fragmentation is something that our behavior suggests that we like it. Some casual thoughts. We have predictive capacity in the weather and climate portfolio that is reasonably classified as climate modeling. We have set up artificial and damaging barriers between weather and climate modeling and weather and climate science, as well as between what we call research and what we call operations. We have placed an enormous amount of effort in CMIP, and this was done in the context of something called the two-center policy, which I'll explain in the next view graph. We have allocated substantial and scattered resources to tailor CMIP products for a variety of climate applications. For instance, downscaling. As I recall, Catherine Hayhoe in about 2012, 2014, did a review of how many people were doing downscaling, and that number was in the 230, 250 in terms of groups doing downscaling at that point in time. We have a relationship with high-performance computing that, in my experience, is somewhat dysfunctional. Again, 2 points I want to state here to reemphasize this relationship with computing. I think it has an outsized influence in how we think about modeling, and we have set up damaging barriers between weather and climate modeling as well as between research and operations. So what was the two-center policy? So that report that I was the lead author on for OSTP in 1999 was taken up by the Bush administration. The report that came out from the National Academy at about the same time. And there was a prevailing sentiment at that point in time that the U.S. should not develop models for assessment. We had this idea of science being out in front, science being somewhat of a holy grail, and if we did excellent science, then assessment would follow. There were, however, a lot of really unhappy people because the first U.S. National Climate Assessment came out at that time. People like Rosina Beerbaum worked very hard to get it out in the Clinton-Bush transition. It did not get a lot of publicity, but there was one thing about it. There were no U.S. models to support that assessment. There were models from Canada, models from the UK, and there were a lot of unhappy congressmen at that point in time. So the Bush administration decided on a two-center policy with, borrowing words from the United Nations, common but differentiated responsibilities, as well as a mandate to cooperate, and those two centers were NCAR and GFDL, and NCAR at that point in time was partnered with DOE. There was a lot of machinations at that point. I remember hearing from Tim Killeen, a number of others, but both centers decided at that time to take on CMIP as something of their operational product to give them relevance to the IPCC. And there's a lot of language that CMIP does not do simulations for IPCC and vice versa, but there's a relationship between the two. And NASA did as well at this point in time. But NASA was not part of that two-center policy. They were more part of the mandate to cooperate. So, what I'd like to say and put here at the beginning, CMIP has been incredibly effective and important. I believe that, and I teach this in public lectures, I say it has given us historically unique information, knowledge of the future, which gives humanity the opportunity to affect our future in ways to establish positive outcomes. And I wrote a review paper at the invitation of some philosophers on the validation of climate models, where I do a brief history of why that is true, and really in that the importance of CMIP and more generally model intercomparison projects in our field, establishing the credibility and the relevance of the field. And I will make the case. I will make the case that CMIP simulations are not the right type of simulations for adaptation planning. That my computer is muted? I'm muted and my volume is all the way down. It only happened that once here. Okay. Well, it's set up in such a way that I have to get back to this. I have to escape in that, and I am muted. So, something I've checked about 5 times because we've been doing this for a while. Let me get back. Let me go into slideshow again. And should I keep talking? Okay. So I'm going to make the case that CMIP simulations are not the right type of simulations for adaptation planning. Should we continue to do things the same way? So I'm going to pose some questions. Are our approaches to weather and climate modeling the best we can do? People write passionate letters to government officials on that subject, and they say no. Are there rational approaches to improve the effectiveness? I think the answer is yes, there are rational approaches. Are we capable of implementing them? That's a different question. Within the weather forecasting community, the unified forecast system, which I have deliberately left the word NOAA off of that, is such an effort because officially right now, the unified forecast system is community multi-agency, and there's a formal memo of agreement between NCAR and NOAA on this, such that it's more than just NOAA. Climate modeling. If I look at the current CMIP, I would ask, do we have a 4+ policy? DOE is no longer part of the NCAR aspect of it. NASA has at least 2 modeling organizations contributing to CMIP. And I would say, as in part of the country I come from, there's been some backsliding on this. What I'll pose more concretely is CMIP an appropriate organizational framework on which to focus U.S. climate modeling activities? Is it sized appropriately, which may be the ultimate and actually most difficult thing to deal with? If yes, then all is good. If no, then what should we be doing? So now I'm just going to have a bunch of issues to consider. I'm not going to go through all the view graphs all the bullet points. But the issues to consider if I were thinking about this strategically is what portion of our intellectual, financial, and computational resources should go towards CMIP. And then there are a lot of questions down there that would, I think, follow from that. Computational resources, high performance computing, exascale computing. What is this role of this biggest computer fascination here and this idea of ultra high resolution? Again, should I keep talking? Okay. And then the fit of models to technology and the fit of technology to models. There's a whole lot of discussion about GPUs in modeling right now. I've had that exact discussion 10 years ago, and I've had the previous version of the discussion on programmable field arrays, array accelerators, and the death of Fortran in 1998. So there are ethical and social justice considerations, which is something that, as Balaji and Monica and I have talked about this more, on who owns and controls knowledge generation, interpretation, and use. And there's some very interesting aspects of CMIP that lie on both justice and injustice side of this, which is not going to be part of this talk. Model development. Who should be out in front in model development? And should they be the people developing the models, the disciplined scientists, or should applications be defining what we do? Should this idea of big computers, exascale computers, have the role that it has within modeling strategy? So, issues to consider, these are the last ones. The foundations of model-based science versus natural science. If you look at model-based science, models are designed for purpose, they are designed for application, and that then gives you the criteria for evaluation, verification, and validation, and the determination of being fit for purpose. And then finally, this usability question. Do model developers and model data services know how practitioners who might find their simulations usable actually use the simulation data? And, do the people doing model development, know the attributes that contribute to usability, and are those criteria being addressed in the evaluation of models? So all those issues there. And then I'm going to come down to posing this is CMIP an appropriate organizational framework on which to focus U.S. climate modeling activities? I'm going to have a use case, which is going to be our experiences in the Laurentian Great Lakes. They're the Great Lakes that many people know as the North American Great Lakes. Some people even occasionally make the gaffe of calling them the U.S. Great Lakes. But if you write papers on the Great Lakes, you're quickly educated. They are the Laurentian Great Lakes. I'm going to focus on adaptation. I'm going to focus on usability, and I'm going to focus on the attribute of credibility, which I will define to address adaptation. The space and time scales I'm going to talk about are different than what many people talk about in climate change. The time scales are 10 years. 30 years is probably the sweet spot of adaptation planning. We are faced now with a very difficult problem, both practically and behaviorally, of the non-stationarity of climate. Climate is changing statistically by any standard definition every 10 years at this point, and it's not stopping. We are faced with the problem of managing uncertainty. My most cited paper since leaving NASA is on something called the uncertainty fallacy, of the idea of reducing uncertainty. So that's the fallacy, that we need to reduce uncertainty in order to make usable climate information. The spatial scales are regional or smaller, and they are defined by politically, economically, or geographical attributes. So some definitions on usability. So the first is usability. Scientists, I did this for a long time until it hit me that we were actually falling into a political trap of arguing that what we do is useful. We often make that argument when seeking funding. We often also make the argument that we're going to reduce uncertainty. And the question comes back is what we're doing usable and in fact used? So usable is defined by practitioners who actually take up the information, the knowledge, and use it. And a review that one of my students, Luni Orial, is working on right now in progress, finds that when you look at a particular technique called scenario planning, which I am a practitioner and perhaps an advocate of, is that projections are inconsistently utilized and underutilized. And what starts to emerge from analysis of that work, it's really because the practitioners are finding that information is not usable. So, some definitions. Cash et al.'s 2003 paper do a lot of defining of knowledge systems and the attributes of usability. Cash et al. Come to legitimacy, which is an attribute of objectivity, fairness, and a lack of political bias. This has been attacked a lot in the last 8 years or so, but I'm not going to talk about that. Credibility as an attribute of scientific adequacy, that is the one I will end up talking about. I will remind us what credibility means before I go into that. Salience is the one that scientists have worked the most on. So things like putting things into GIS formats, things like downscaling, have been scientists' efforts to make things more salient, and meaning essentially, are they relevant to the problem to be addressed? In our research, we have added plausible scenarios where they are being physically consistent or realizable. Bruce Hewitson has done some very nice work on plausibility and ethics. And what we do is we try to reframe this as thinking as a set of plausible futures rather than focusing on probable futures. And that recognizes that there's no one outcome of a warming climate. We hear all the time that climate will make hurricanes, quote, more intense, whatever that means. But hurricanes have a whole variety of behavior. All those different variety of behaviors are going to change because you've got more energy in the system. And so saying they're going to be more intense, which technically means the wind's going to blow more, is not very useful, nor is it correct. And then the ethical considerations include recognition and consideration of issues of equity and social justice. And then more and more importantly, scientists neither understating or overstating our confidence about what we know. So those are the attributes of usability. Another thing that became very apparent to me working with actually the unified forecast system and actually listening to how forecasters work, and I will say in the field of weather forecasters, they often go, we don't understand at all what the model developers are doing it and why they're making the decisions that they're making. They're not really helping weather forecasting, whatever they're doing. And one of the things that becomes key, and if you actually look at NOAA sort of official documents, they're not providing model forecasts, they're providing model guidance. And the forecasters then are the experts who are taking observations and theory and putting them all together to generate weather forecasts. So the model's taking on this role of guidance and helping one to think, I think is an important framing that we need to get. In the Lemos and Rude paper on model on predictions and projections, we talk about using the word projections is better than prediction. I would now go, and we have been trying in our more recent papers to move to this idea of guidance. And I can assure you that reviewers get upset when we take it down to that level of, let's say, participating with these other sources of knowledge and information. If you're interested in weather forecasting, the Model Evaluation Group at the Environmental Modeling Center has weekly summaries or analyses of particular forecast situations. And if you listen to them, and especially, they're available online, but you do have to ask for access to them. The ones on Hurricane Michael and the Northwest heat wave are really remarkable case studies of how forecasters use modeling information. So that gets you to this portfolio of models. A hierarchy, an ecosystem. I don't like hierarchy because it values things, much like a management structure and an organization, gives a hierarchy. I like the idea of an ecosystem. But if you look at weather forecasting, they're global models that are deterministic and probabilistic. They're regional models. They're phenomenological models. There are impact models, process models, and then there's post-processing and tailoring. And that list over on the right is what these models are being used for. And I will ultimately pose that the same sort of approach is needed for adaptation modeling. So the Great Lakes, these are the Laurentian Great Lakes. This is what they look like. And when you start to use them as a use case, one of the things that you immediately find is the Great Lakes, there's a strong focus on water and presently water abundance. When I say water abundance right now, I mean because there's been a lot of flooding there, because there's been a lot of rain. There's also been changes in the seasonal runoff. The list could go on, but also a real focus on water because there are people starting to write editorials that say the Army Corps of Engineers should be already planning to move this water to the Front Range. It's a lot of water. So, the use case. What I'm going to do is say there's a challenge to credibility here. Again, credibility is an attribute of scientific adequacy. I'm going to go through three aspects of this very quickly: bias and bias adjustment. A colleague at GFDL, whose name I cannot remember right now, unfortunately, he and I were giving back-to-back talks at a meeting on adaptation, and he opened his talk that we need to get rid of this word of bias correction because you're not correcting anything. It's bias adjustment. The question becomes, how large is too large? And another question then becomes, how does that adjustment compare to the physical terms in a variety of conservation equations? The next thing is the representation of weather scale processes. Weather is very intuitive to practitioners. Weather is how we feel. Climate, damage, vulnerabilities. And then structural deficiencies. For example, the Great Lakes. Do the models have lakes in them? It is really hard to talk to the mayor of Buffalo, the model that does not have a lake in it. How are the lakes represented? Does the weather respond to the lakes? When we first started this, I called some of my colleagues, some of them here, some of them have since left, and they immediately said to me, well, the lakes are not important to the global climate. And they also said, and these weren't designed for adaptation. And I felt that was a little bit of a disingenuous answer because they were being used for adaptation and they were clearly being justified for that. So how might we establish the credibility of models in adaptation applications then becomes the question, because they are our source of information. We cannot just not use that knowledge and information. So here's the bias part. Interesting plot to be showing at CESM. But what we did here is we took 65 models from CMIP 5, North America Cordex, and University of Wisconsin CM4, Reg CM4. We looked at temperature from plus or minus 5 degrees centigrade, precipitation from plus or minus 50% errors in the basin seasonally. So one, if you count, this is not all 65 models. If it's white, then that's good. If it's orange in precipitation, then it's too dry. If it's orange in temperature, it's too hot. So droughty situations. Interestingly enough, the suite of models that have CESM written in front of them do pretty well on precipitation in this case, but I would not take that, generalize it. So they're the sort of the idea of what the models are. We summarize this in tables like this, where we've taken the worst season out of each model. And in this table, what's shown here across the top are the seasonal temperature bias. And here's the seasonal precipitation bias. If we were to select models with a 2-degree temperature bias and a 25% precipitation bias, then our ensemble has 3 members in it. If we were to take all 65 models and look at 100% precipitation bias and a 5-degree C temperature bias, 5 of the models don't even get there. So these models up in here are maybe reasonable to be using, but sort of at the beginning of the process working in the Great Lakes is water budget. And in any of these models, if we were to calculate the net basin supply, we get 100% errors or more in net basin supply and 100% errors or more in each of the components, precipitation, evaporation, and runoff of net basin supply. And in particular, systematic giant errors in evaporation, which led, I think, probably falsely to the statement 10, 15 years ago, the Great Lakes would dry up. If they are, they're going to dry up in 100 years. They're surely not drying up right now. So this is a starting point, net basin supply. And the errors here are so large that we just did a report for something called the International Joint Commission, which manages the Great Lakes. And we actually put a disclaimer in that report that they should not be using these models for quantitative work in terms of managing the lakes. They disliked that so much, they made us put it in an appendix rather than an introduction. Next thing, what's the role of weather? Andrew Gelman and I had coffee on Friday, and this is one of the things we were talking about is what seems to be a sort of constant battle between weather and climate in the U.S. And, you know, when it gets right down to it, weather's really important to climate, might even be in the WMO definition. But what we found working with cities and tribes and NGOs and the folks that we worked with, and we've worked with about 100, 150 organizations at this point in time, is that they have three questions at the beginning: what has happened, what will happen, and then they like to talk about the vulnerabilities that they have already realized. This became a much bigger issue in the Great Lakes after Duluth sort of exploded from below in a huge flood in about 2010. But when you think about vulnerability, you immediately get to weather, because this is how we feel climate. And so within the first couple or 3 years, we had this algorithm for engagement, of which the third part of it was model evaluation and how well are weather scale processes represented in the models. And this became very focused on precipitation. And you know, what you immediately see in precipitation there is, with all these models, a strong bias. It's usually a wet bias. It varies with geography, which makes things worse. But from a process weather point of view, winter, you have cyclones. So that's better representation than summer. But the summer precipitation was not represented with really any fidelity because of the long-standing problems of dealing with mesoscale convective complexes. And you know, these are modeling flaws that many people were aware of. I remember talking with Julio Bachmeister about them when we were originally doing this work. And one of the things that comes out of this from the point of view of a practitioner is, aside from not being able to say, well, we can't actually simulate what caused the dam to fail in Midland in these models, your uncertainty is different in winter than it is in summer. And it makes it very hard to describe, because we have process-based uncertainty in the summer that's worse than it is in the winter. So again, this brings, I think, one of the essential nature of models for adaptation. You have to be able to talk about weather. It's how we feel climate, and weather impacts are what we need to plan for. Focus on the weather features improves the uncertainty description, and how weather changes is a good way to interpret regional attributes of how the climate is changing. For example, one of the easiest things to talk about with regard to hurricanes is how much wetter they are. But there's a lot more moisture in storms, and the possibility of storm tracks having changed will move weather in a region in a way that makes sense in many ways to many people. So, and that gets us down to this last one I'm going to talk about. Structural uncertainty, structural deficiencies. Lakes, how well are they represented? And lake effects, of which the one that everyone thinks about in the Great Lakes region is the strong lake effect, precipitation, snow, and how well it is represented. I did a long interview yesterday with Yale Climate Connections on whether or not lake effect snow would disappear. An interesting question to think about on 10, 20, 50, and 100-year time frames. But another one is lakes suppress precipitation in summer because they're cold, especially Lake Superior. But if you look at a lot of models, some reanalyses, at least 6 years ago, they have nice moisture-driven maxima of summer precipitation over the lakes. So, but no one looks at it. So in a paper that Monica mentioned in the introduction, a Briley et al. Paper, we came up with this big algorithm for finding lakes in cement models. And I'm not going to go through it, but it gets to sort of every aspect of how modeling centers are building things and documenting things. Lakes, it's counterintuitive to a lot of people that when you want to know about lakes, you start with the land component of the model. Some people use the ocean models in the lakes. Some people, 10 years ago, had wet ground. There were occasionally times when the lakes would be, here, and the atmosphere above the lakes would be over here. So they weren't even talking in the right geographical area. So we looked at all those models, and I think we came up with something like 5 had lakes, and then there was the question of, are they actually providing a lake effect coming from them? So the point isn't scientific here. This was very frustrating and revealing. It took more than 3 years to do that lake study. And in the process of that, we went from CMIP 3 to CMIP 5. So practitioners are saying, are the new ones better? And then after that, more than 3 years, then how are the lakes actually treated in the models? Then we have to establish whether the lakes influence the weather. The answer is poorly. We get to that step after evaluating do the models represent weather with fidelity, sometimes. And then we are faced with the problem that those bias adjustments are not defensible. And this would be perhaps okay if it were a research model that really was not being used for adaptation. But when it's a portfolio of 50 or 60 models that you're analyzing to form an ensemble, because that's what we've been told to do, this is an amount of time that is really not justifiable at this point in our history. So when we get to time, this is something I invented years ago in my problem-solving class, where when we started the class, I want to know what is a short and a long time. So from a practical aspect, 50 years is a long time because that's a human dimension. It's the length of an infrastructure investment. It's the accumulation of wealth over a lifetime. If I talk about this in detail, I say, the economy and energy security always trump climate change in terms of being a priority. There are short-term issues important to climate change, including in the US. You can see the huge effect of elections, but that's not the point here. Here's another version of this, thinking about adaptation, planning, permitting, implementation, and use of a piece of a bridge, a drainage system over 0 to 50 years. But now we're at the point climate is changing on a decadal time scale. The customers of this work are actually saying 30 years is a ridiculously long time to say average weather for climate. It's not relevant to me anymore, and what it was 50 years ago is not relevant to me. CMIP changes on a half-decadal time scale. Evaluation and use of CMIP is on the same time scale but lagged. So in the timing of planning, permitting, and implementation, we're still evaluating some old models here. And then non-stationarity is requiring replanning once we get information. One of the things that really triggered me on this was Denver Water, which is an organization that has been quite proactive in thinking about climate change, building some dam, not wanting to go back and reconsider climate with regard to that dam's plan because it would completely cause them another decade in permitting. So, is CMIP an appropriate organizational framework on which to focus U.S. climate modeling activities? I would say as a whole, no. There are important roles for that type of modeling, and it should continue to be done. We need models designed and built for adaptation and other applications. And the other application I think is most critical is geoengineering, because it's going to happen. There are going to be people proposing it, and the fidelity of our models to address that are not up to standards. And then there are a number of other lines of reasoning besides this credibility and structural aspects that would have a good manager thinking about CMIP. So, framing a plan. Remember that the foundation of model-based science, as opposed to natural science, is that models are built for purpose, understanding how model guidance is used, usability, and I would assert at this point, applications should have a stronger role in defining design criteria of models, and they're just as importantly, the simulation portfolio, the design of the simulations that are needed. And the challenges of adapting to climate change, I think, impose ethical obligations to develop this capacity. Going back to this, remembering that model guidance, and the red arrow here is to state that I replaced deterministic with process, but forecasting at weather scales and a variety of climate scales is needed throughout this sort of what I call a dynamic ecosystem at this point in time of capacity that is needed to address adaptation problems. Reanalysis has a surprisingly large role in here, and things like machine learning and looking at types of weather patterns and things like that. So, if you look at this portfolio, this is really off the top of my head. The global model has a limited quantitative role because they have limited quantitative value. I frequently quote Steve Schneider, who said that a lot of climate modelers were looking for something that he described as crackpot accuracy. So where we are at and what we do, plausible scenarios is what we're looking for from the models, and uncertainty management. Think of those models designed to go into regional models, or perhaps having embedded regional characteristics associated with it. Does that improve bias? Our evidence with Cordex is no. But it does give us weather scale information that provides better uncertainty management. And then the importance of a whole variety of models to tailor information to any particular adaptation application. And what I would like to say is that these models are to help you think. They are not to provide answers. You'll notice that uncertainty management is part of each one of those. That's what you're doing there. So, finishing. I hope I haven't gone too long. First one here is just a restatement that models are built for a purpose. That is an application. There are the reasons why we need to do that. I'll just say Cement models are built for understanding. That's off their website. This is a broad purpose. It's open-ended. They've done it very well to contribute to that. But we are trying to adapt models built for other purposes to other applications. We need a modeling capacity that is focused on adaptation, a possible systems design. Again, this is, relatively naive, is this idea of a portfolio that's somewhat similar to the weather process. And the weather people are not that well organized. That's why the unified forecast system came into being for in part were the 12 or 15 regional modeling products. So takeaways. Again, I'm just beating this to death at this point. We need model capacity design for adaptation applications. I'll say our modeling enterprise needs to be adaptive. We need models that are really designed and documented for these purposes. It's unacceptable to take 2 or 3 years to answer that question. I will say in credit of the many things about the modeling activities at NCAR, they were the best documented of any that we found. The community aspect of the NCAR modeling activity has made it a remarkably unique and valuable resource at this point. Effective design requires knowing how model guidance enters into problem solving. And one of the things, if I had influence in policy, I would be talking about an environmental security council and the need to have environmental security as something out in front, and that we needed a modeling capacity to support that. And with that, thank you. The view graphs contain all of Laura's papers as well as some others. And again, I acknowledge, I didn't get Andrew on this one. I acknowledge the folks I've been talking to and some of my more philosophical works on this subject. So thank you. And I think when I spoke in here last time, there was a clock up there.
They took that down, unfortunately. We're a little bit over 12, but to possibly make up for the fact that we had some technical issues we had to navigate, I'm going to open up the floor to see if there are any questions. Yeah, Katie. This is going to be fun. Thanks.
Thanks for your talk. That was very interesting. I wanted to come back to what you said about reducing uncertainty and shifting away from that framing at the beginning, and then also your mention of uncertainty management at the end. Maybe could you expand on that?
So I'm trying to register myself to not run on too much, because I can, on my Open Climate website, I have a whole course, a mini course on uncertainty framing and management. So the uncertainty fallacy is that scientific uncertainty needs to be reduced in order for the climate information to be usable. It's a fallacy for a number of reasons. One is, compared to other sources of uncertainty within most problem-solving paradigms, climate uncertainty is the smallest. We have quite definitively given usable knowledge going forward. Think of economy, think of who's invading whom, think of the built infrastructure. It's what you know best. And so in the context of actual decision making, that's one of the issues. The next one would be, it's a complex problem where we're unpeeling things, and it's very unlikely that as you unpeel, what's going on with root systems and then deeper soil or into glaciers and learning more about calving, it's very unlikely you're going to actually reduce uncertainty. You're going to introduce more uncertainty sources for sure. And it's very unlikely. And the third one that I mentioned is throughout the 90s into about 2005, there was everybody said in their proposals, well, we're going to fly this satellite mission, we're going to do this modeling because we're going to reduce uncertainty. And then the politicians started to, they were smart. About 5 years, we need to do this next mission to reduce uncertainty. And they said, well, what uncertainty did you reduce with the last mission? And then you would go through, well, it's not very likely doing a scientific problem that we're going to reduce uncertainty. Then why are you saying this? So you're falling into a political trap. Do it. So those are the three in terms of what the uncertainty fallacy is. The uncertainty management, we've ended up with the scenario planning approach, which we tend to do 4 scenarios, 4 management scenarios for a particular management problem. With that uncertainty, we like to bracket perhaps with climate. Then you take and you put the climate, you put something disruptive in it like forest fire or wind-blown forest damage. How does the forest recover? It's in a new ecosystem because the climate has changed. Now it's been disrupted. And the fact that there's no one outcome, that comes. So we're using scenario planning to manage that uncertainty.
Thanks. Yeah, I guess I would argue that CMIP models are used for more than just understanding. So I'm wondering what your perspective is on, if you don't have some projections of large-scale feedbacks, climate sensitivity, and the large-scale circulation, where would you even start for trying to downscale impacts in the Great Lakes region?
So again, I'm thinking a little bit. So one, I don't want to come across as bashing CMIP, and so as I've framed this, I've tried to take that in another way. We need global models, and I think it's not the model as much as the scope, the size of the experiments and the simulations associated with them. There's nothing fundamentally flawed in the model. It's what we're trying to do with the model. But what I think, and this became apparent when I reviewed probably 30 proposals for the Copernicus Climate Service, is the effort there of developing at least one model focused on adaptation and at least one model that is, as a corollary to that, focused on decadal prediction and focused on what's going on in the ocean and starting to put the ocean at the center of that problem. And as another corollary to that, since sea level rise is something we're going to be dealing with, focusing on what surrounds that to give us better information about sea level rise. I hesitate to say that because I sort of said it at Stanford. Then people said, well, we don't want to get the decadal prediction people energized again. So there is global modeling. I think the time frame is shorter than the 150 years. I think there are many attributes for that model that need to be advanced that are not advanced in sort of the normal CMIP simulation design.
So my question sort of is how to project this onto the human enterprise of model development. Mm-hmm. And I largely subscribe to your thesis that we're not as effective as we could be, and that specific questions or requirements for models provide clarifying motivation to ensure that the model provides a defensible representation of the phenomenology of interest. But I wonder about the potential degree of fragmentation in the sense, what is the possible set of adaptation questions? How large is that set? And can a modeling center build bespoke tool chains that support that collection? And how do we balance this idea of phenomenology and process-oriented modeling with extending it to support adaptation applications? Is precipitation quality in the Great Lakes region antithetical to high quality simulation in some other part of the world? Are there trade-offs in that space, and how to manage building tools that support the full collection of adaptation questions?
So part of that question was Great Lakes versus somebody else, which is actually one of the many ethical questions. And in fact, if you look at the current models, it wasn't that long ago that the Southern Hemisphere was much more poorly forecast than the Northern Hemisphere, which I would say is actually that sort of bias coming out in it. So that's an interesting one. So I will say your question of how you do the balance ultimately troubles me the most, because I do not have, based on a lot of experience, more than anybody else that I'm aware of in the field of changing organizations in our field, I do not have a lot of confidence in how to do that. I deliberately have not said what I would do if I were king of the world, because I'm, never going to be the king of the world, and even when I've had some influence, it's been very hard to change those things. But I would say now that we've gone from 2 to at least 4 people, 4 modeling organizations invested in CMIP, it's going to be even harder to move them. And I don't know how to do that in the US. I think they're doing it in Europe. I don't think it's as easy as it was in 1985 when they formed the European Center. But I say we are 2 generations behind what's going on in Europe, and by 2 generations, I mean 2 5-year modeling proposal cycles of what's going on in terms of developing adaptation capacity modeling. So I have a lot of opinions on that. One of my 4 retirement books is on management of scientific organizations in the United States. So.
Sorry, we're going to take one last question from Bill, and then we have to close it down because we're running over. Go for it.
The question I had is maybe the one you just said you don't want to answer, but if there are 4+ CMIP models and we need more adaptation, maybe geoengineering models, is it easier or more feasible to steer the existing centers in that direction, or to make whole new centers focused with a new focus on adaptation?
Another question I've thought about a lot. One of the problems you have with making a whole new center is that you've got a limited expertise base. And so you're going to have to make a whole new center out of the same people at some level if you're going to do it quickly. I have written documents proposing whole new centers, and one of which imagined the U.S. federal agencies as member states in the same sense that the European countries are member states of the European Center. In practice, I've tried disruptive incremental change within existing organizations. And there are a lot of built-in structural deficiencies in the way we fund and manage science that make that really, really hard. And the best paradigm, and this is going to seem insane, that I've ever heard to deal with this is the case study of changing the culture of sexism and racism in the Amsterdam Fire Department and Amsterdam, Holland, and listening to them talk about the cultural change, the leadership, and how to deal with the changing politicals around them. And it's tough. You know, I just did 4 years with NOAA, and maybe Neil Jacobs can carry it forward. We talked about it a lot. But you know, in NOAA, when you have program managers who are sitting there on 120-day cycles because they can't put permanent people in them, and each one has to reinvent the program in their own image in order to get promoted, it's fundamentally undermining.
Well, we might end it on that.
Cheery note.
Yeah, thank you. So thank you very much, Ricky, for joining us for the first in-person seminar after COVID. And like I said, he will be with us for lunch. So if you want to continue this chat, just come to the Mesa cafeteria. Thank you.
And sorry it went long, but thank you. Sorry it went long, but there were a number of stops for technology.